So the last 4 videos all dealt with electrophilic aromatic substitution, and so I thought it might be helpful to finish off with a quick video of a couple example problems. Alright, in these first examples, we just want to determine what reagents we would use to accomplish the following reactions. So in the first one, we have chlorination, and so we're going to want to use Cl2, and then we need a catalyst, and the catalyst we used previously was aluminum chloride. To add the SO3H group, this is the sulfonation, and so this is where we needed to use the fuming sulfuric acid. So you could either write fuming sulfuric acid, or I like to write concentrated H2SO4 and SO3. Alright, now this is one we're going to need to do it in a couple steps. So we didn't learn how to add an amine group directly to the benzene, but we did see how we could add an NO2 and then reduce that to give us the amine. So to add NO2, we're going to have a mixture of nitric and sulfuric acid. That's going to give us the nitro group. And then to reduce that, we're going to use iron with HCl in the first step, and then hit it with sodium hydroxide. And in this step, we could have used either iron or zinc. Okay, here's another example. At first glance, it looks like maybe we would want to use Friedel-Crafts alkylation, but to do that, we would have to add, as an electrophile, a primary alkyl halide. And we learned that those are no good because they're going to rearrange to give us a mixture of products. So in order to add something like this, we saw that first we could do the Friedel-Crafts acylation, and then we could do the Clemmensen reduction to get rid of that ketone and leave us with the alkyl group. So the reagents that we're going to want to use to accomplish this so my intermediate that I'm going to want to make, I'm going to want to have 1, 2, 3, 4 carbons. And of course in the Friedel-Crafts acylation, I'm going to have that ketone. So the compound I'm going to want to react this with is this, and then I need the Lewis acid catalyst. So I'm also going to need the AlCl3. So that will accomplish the Friedel-Crafts acylation. And then for the Clemmensen reduction, I need the mixture of zinc and mercury along with HCl, and that'll get rid of the ketone and leave me with the alkyl group. Okay, so finally, we want to predict the products of this reaction and then also draw the mechanism, right? And we've seen this mechanism 10 times over, and so I think you can be pretty sure on quiz over this material or on the test, this is going to be one of the mechanisms that we ask you to draw. So first, my product, this is going to be Friedel-Crafts alkylation. So I'm going to install the alkyl group where the chlorine is onto the benzene. And so that should be my product. Finish off the benzene here, of course. All right, so for the mechanism, the first thing I need to do is show how I'm going to activate this alkyl halide with the Lewis acid. And so for that first part, So the chlorine on my alkyl halide is going to act like a Lewis base. The AlCl3 is going to be a Lewis acid. That's going to give us this complex. And then essentially the AlCl4 minus pops off as a loss of a leaving group. Giving me this carbocation. All right, and so now that we have our electrophilic group, let's see how that's going to attack our benzene. Go ahead and draw in the hydrogen that's going to end up being substituted. So pi bond from the benzene is going to undergo nucleophilic attack onto our electrophile. And this is going to give us our sigma complex. Now remember, the sigma complex is resonance stabilized, and we need to show that in our mechanism. So we can move that, we have an allylic carbocation, so we can move that positive charge around our ring and get two additional resonance structures. All right, so this is my sigma complex. And then in the last step, we have the proton transfer. And that doesn't look very good. Let's clean up that negative charge a little bit. My pad isn't recognizing the pen down this bottom region of the screen very well. All right, and so for the proton transfer, the chlorine steals that hydrogen. The carbon-hydrogen bond reforms the pi bond here, which is going to restore the aromaticity. And then our final product and we finished our mechanism.